G'day all, this is going to be a slightly unusual video in which I'm going to kind of talk you through a website a little bit. I haven't created a video of the standard model in the materials that I was drawing from to build this course because it wasn't part of the old Queensland senior syllabus. It's new in the new syllabus. It's probably a good thing that's been added, I think, because it basically is one of the big ideas of physics, and it's quite a current one. The work was developed really sort of post the 1960s, which, not so much for you guys, but that's within my lifespan. This is relatively recent work. So just talking a little bit about the standard model of particles. If you check the URL on the screen there, physics.info/standard. So there's lots of info on this page, way more than I'm going to go through in any detail today. There are also a number of fairly good YouTube videos ranging from about 5 or 7 minutes to about 20 minutes to about an hour talking about the standard model. They are good, but they all take quite different approaches to each other. So it's actually reasonably challenging to get your head around the details of it. And there are a number of features in the syllabus that are important to talk and think about in terms of really understanding the standard model. Now, again, some of you may have done courses while you're at uni that have gone into it in much more detail than we will here as well. But just a little bit of a rundown at least. So there were a very large number of particles named and mentioned in the hundreds, and it was a very confusing time in the 60s, and Murray Gell-Mann, who ended up with the Nobel Prize for Physics, started to simplify and organize that in a way similar to the way that Dmitry Mendeleev organized the chemical elements into the periodic table of the elements. Gell-Mann originally developed a diagram called the Eightfold Way, and then that moved into the standard model. So essentially, the standard model is made up of a number of different particles that that are the building blocks of matter and material. So normally we think about matter being made of protons, neutrons, and electrons. This is the next level down. So the subatomic particles, if you like, the particles that make up protons, neutrons, and electrons, and the other various exotic particles that we deal with. So if you see in this diagram, you've got the electron as one of those fundamental particles. So the electron is not made up of these other ones. It has a related neutrino. The muon and the tau also have their related neutrinos. So that is one set of particles called leptons, I believe. I guess that's the other thing. I haven't made a video on this because it's a long time since I spent a lot of time on it, and it's probably evolved since I did as well. So I'm going to do my best. But all care and no responsibility. You should read up and study up on this particular topic yourself as well. So there are the leptons, electron, muon, and tau particle, and their associated neutrinos. There are the quarks. So different people pronounce it quarks or quarks. I find quarks easier to say on the regular. So those are in pairs, and you are required in the syllabus to know their names. So up, down is a pair. It's easiest to remember them if they're in pairs. There are 6 of them, up and down, opposites. Charm and strange, not so much, although you might think that if someone is strange, they're less charming, and vice versa, although depends how gothic you are, I suppose. And top and bottom. So there are the 6 quarks up the top here, and then there are the mesons, which are the particles that mediate the various forces. So gluon, photon, W and Z particles, and the Higgs boson. So let's just go down. Here is a reasonably good and rich table, and that's probably the most useful thing on this page, I think. Sorry, my microphone's getting in the way of my stylus here. Okay. So we've got a bunch of info here. You can see the quarks is this area here. And as we saw above, the up, the down, the charm, the strange, the top and the bottom. You can see when they were discovered. So from the 60s, 1964, completely coincidentally, was the year I was born. So all of these are as young or younger than me. And they were actually, I guess this is predicted in 64, discovered in 68. And so they've all been discovered over relatively recent times. The quarks have spin number 1/2. They have charge in terms of electron charges. So the electron charge, 1.6 by 10 to the minus 19 coulomb, is this unit of charge. So the up quark has plus 2/3, down quark has minus 1/3, etc., etc. They have color. This is quantum chromodynamics, which we won't get into at all and is not gone into in the secondary syllabus. But color is also conserved, as well as charge and spin. And then they have their mass in units of mega electron volts per divided by c squared. So if you remember Einstein, E equals mc squared, and you rearrange that to make m the mass of the subject, so you get m equals E over c squared. So this is an energy in mega electron volts, which is an energy unit, divided by c squared. So those are those masses. Because obviously kilograms are not the right kind of unit for things that are much, much smaller than atoms. When you think about spin, don't think about physical particles that are rotating and have rotational energy and so on. Spin is a name for a physical quantity that is conserved and that is measurable. But at the same time, these particles, really, we think of them as mathematical points with no volume, zero volume, one-dimensional. So they can't really spin in the sense we think about. So spin is just our quantum number, essentially. And then we have the leptons down here. You can see that the quarks plus the leptons are all together make up the fermions. So you've got the fermions there. And I have an awful feeling that I called the bosons mesons. The bosons are these contact particles, so I do apologize for any confusion that I've caused there. So we've got the fermions and the bosons. So let's continue with the fermions. We've got the leptons. We looked at the quarks, so there are 6 quarks. There are also 6 leptons, the electron, muon, and tau, and then their relative neutrinos. So that's 6 altogether. Again, you can see when they were predicted, when they were found, the electron much earlier than the rest. Basically, the earliest of all of these, J.J. Thomson discovered the electron back in the 1890s. You've got the muon and the tau. They are also spin 1/2. And you can see their charges are whole numbers. The electron, as you know, has a charge of -1. The muon and the tau likewise have a charge of -1. The neutrinos have 0 charge. We know that neutrinos are very, very tiny. They have very tiny masses relative to everything else here, and they're very hard to detect because they don't have charge and they don't have much mass, so they just go through everything. So we've got the neutrinos. The proton and the neutron are not fundamental particles. The proton and the neutron are our very common, well-known particles, but they are made up of quarks. They're made up of up and down quarks, and the proton has charge +1, the neutron has charge 0, as you know. They have very similar masses, not identical, but very similar masses, and they have charge spin 1/2 as well. So you can see that basically all of the fermions have spin 1/2, and the bosons have spin 1, except for the Higgs boson, which has spin 0. Now, let's just figure it out, because the proton is made up of ups and down quarks, and it has a charge of +1. So we can actually just do some maths. So if we go up to the up and down quark, and we've got charge +2/3 and -1/3, so we need to add those up to get a total of +1. So I think it is 2 ups and a down. Does that make sense? Because that gives us 4/3 -1/3 is 3/3, which is a 1. Right? So if you think about the proton being 2 up quarks and a down quark, that gives you an overall charge of +1. Think about the neutron being 1 up and 2 downs. So you've got +2/3 and then minus one third, you get to zero charge. So the neutron is an up and two downs, the proton is a down and two ups. So I hope that's relatively clear. That's reasonably challenging stuff to deal with. Now, let's just keep on cruising for a minute, and then we get to the bosons. The Higgs boson was predicted back in 64 as well. I think all of the ones predicted in 64 were predicted by Gell-Mann. Peter Higgs was involved in predicting the Higgs mechanism as well. And the Higgs boson was recently discovered, 2012, in the Large Hadron Collider at CERN in Europe, in Switzerland and France. So it's the most recently discovered. It's the most massive. It's 125,000 of those units, when the proton and the neutron are about 1,000 of those units. So it's a very, very massive particle. And the Higgs boson is a really interesting particle. We think it's what causes objects to have mass. It imparts mass to the other objects in the universe. The Higgs mechanism is still relatively cutting-edge physics. So Higgs boson recently discovered. The other bosons mediate forces because there's forces between atoms. So the one that we're most familiar with is the electromagnetic force. That is the force between positively and negatively charged things. And the relevant boson for that is the photon. So the photon, the light particle, is the boson that carries forces, electromagnetic forces. If you have a positive and a negative attracted to each other, or a negative and a negative repelling each other, and so on, photons are involved as the boson that carries that force. The strong nuclear force is the one that holds the atoms together. You remember that we said that the protons in the nucleus are positively charged, so they will repel each other. They will repel each other quite strongly because they're positively charged and they're in close proximity. You need an even bigger force to overcome that, and the force that overcomes that is the strong nuclear force. The gluon is the boson that mediates the strong nuclear force, and the gluons. The strong nuclear force is powerful enough at very short range to overcome the electrostatic repulsion. But what you actually need is more and more nucleons. And so to be stable at the start for, say, helium, you have 2 protons, 2 neutrons, because that's enough for the strong nuclear force to overcome the electrostatic force. By the time you get up to, say, uranium, you have 92 protons, but you have 235 nucleons in total. So you've got about 140-something neutrons for the 90-something protons, because the neutrons have the strong nuclear force but don't have the electrostatic repulsion. So you're piling more and more and more neutrons on so that you've got more of the strong nuclear force to overcome that repulsion as you put more and more protons on. I hope that's clear, and that's part of where this links to the radioactivity information that we're going to talk about. Sorry, I am not 100% sure whether this will appear after the radioactivity information. So you've already talked about a lot of that, and we've probably thought about the binding energy per nucleon, fission and fusion, why the nucleus behaves as it does. And then the W and Z bosons both mediate in different ways the weak nuclear force. The weak nuclear force is related to radioactive decay and the breakdown of various particles. It's a little bit more complicated. It's not a force in the same sense of holding things together. It's a little bit different, but the weak nuclear force is mediated by the W and Z bosons. So there's a couple of other bits and pieces that we need to deal with. You can see them divided there into families. It might be a clearer way to put it. So you've got the fermions with the quarks at the top and the leptons at the bottom. And then you've got the bosons over on the right-hand side. The gluons, the photon, connect the W and Z put together because they're both the weak nuclear force, and the Higgs boson. So we can cruise down here a little bit. There's a lot of text on this page. I thought it was easier to use their diagrams than to try and draw my own diagrams in this case. This diagram is basically the same one we just saw, but with the spin included. So spin a half for the quarks and the leptons, spin 1 for these bosons, and spin 0 for the Higgs, which is kind of separate and different. We'll cruise down here a little bit further. There is a number called lepton number, and all of the leptons have a lepton number of +1, but each of them also has an antiparticle equivalent, as do the quarks. So there are antimatter particles. There is an anti-up quark, anti-charm quark, anti-top. So they're antiparticles of all of these, antiparticles of all of the leptons. There are not antiparticles of the bosons. So a lepton has lepton number +1. So an electron, a tau neutrino, etc. has lepton number of +1. A anti-lepton has a lepton number of -1. So is that clear? So it's how lepton something is. So something is either 0, 1, or -1 level of leptonness. There is also a hadron number, which we'll talk about in a minute as well. Very briefly, and I know this video is getting long and complicated and brain bendy. You can definitely look up this page. I've given you the URL. You can read through it all in great detail and with care, and go to other places as well. But when you get 3 quarks together, you get a thing called a baryon. So there's a number of different baryons, including the proton and the neutron, because remember we just said that they have 3 quarks in them. So they're baryons, and mesons, which is the term I incorrectly used before. But the mesons are made up of 2 quarks, not 3 quarks. So the quarks can go around in 2s, called mesons, or 3s, called baryons. And overall, combining the baryons, the mesons, and the leptons, we get the word hadron. The word hadron means thick, but we're not spelling that with 2 C's on the end. But the hadrons are particles that join together to be larger than individual quarks. So that's why they're called the hadrons. And so we can talk about the hadrons. This excludes the leptons. So the hadrons and the leptons are different families as well. And you can, again, cruise down. You can look at the color. You can look at these diagrams are called Feynman diagrams, and technically you should be able to do Feynman diagrams as well, but that's another video for another day, I think. I will actually probably create a short video that talks about what a Feynman diagram means and how you read it. But in brief, if an alpha particle is scattered from a gold nucleus, which we know from the Rutherford experiment about how he discovered the nucleus. So this is a nucleus of gold. The alpha particle comes in, and you can see that little gamma there is a photon, and that photon is the boson that is putting a force on the alpha particle, so the alpha particle's track is changing. So you can see the interaction. An electromagnetic interaction happens using a photon. Within a proton, you've got your 3 quarks, and the gluons are holding the quarks together. So the gluons are the bosons. Sorry, I've made that mistake again. The gluons are the bosons that hold quarks together in the atom. And this is a decay of a beta particle, which is, it's a decay of a proton into a neutron, releasing a beta particle, which is mediated by the W boson. Now, this is quite confusing, and you don't really need to know it at this level. But as I say, we'll do another video on Feynman diagrams that will give you a sense of what's happening there. It is all quite cool and quite interesting, I think, because as I say, the cool thing is you had hundreds of particles, and now you have this relatively simple system with, let's go right back up towards the top, about there I think is the nicest one. Relatively simple system with 6 particles plus 6 particles is 12 there, 4 bosons there, but we also have the antiparticles of these ones as well. So it's really only 28 particles altogether that allows us to describe, predict, explain, etc. all of the hundreds of different particles, the kaons and the muons and the very tau particles and a very, very wide range of particles and behaviors that we have to talk about. So I'm going to wrap up there. If your head is spinning, that's to be expected, but do have a look at the syllabus document as well to get a sense of exactly what you're required to know and how you can demonstrate that knowledge in relation to the standard model. I will also create a no, I was going to say I'll create a calculations video, but we tend not to do a lot of calculations with these. We might do some things like what we did there, working out the charge on the proton if it's 2 ups and a down or 2 downs and an up, whichever one it was we said. But anyway, I hope that that is helpful in giving you a start, a way in on the standard model. Thanks a lot.